action and reaction forces. So, as we know that about Newton's third law, every action there is an equal and opposite reaction, right. So, every action there is an equal and opposite reaction, hence the reaction is always equal to the action force, right. So, this is action and this is reaction. So, this is action force and this is reaction force, both are equal. So, let us see one example. So, this is the book and I want to keep the book. So, the book kept on the table, and the book pushes the forces downward on the table, that is called as reaction force, and the table pushes upward on the book, that is called as reaction forces, right. Both are equal, that is why there is no displacement, right. Now, instead of book, now I kept the ball on the floor, then weight of the ball is acting downward, this is called as the action force, and wherever the supports are there, we have to consider the reaction force. So, reaction force is always acting upward, which is equal to the action force. So, this is called as reaction force R A, right, reaction force from point A, because this is the support of ball, the point A which is support of ball. So, this is weight and that is called as action force, and the reaction force which is R A, right, from the support, clear. So, the ball pushes downward, that is action force, and the force exerted by the support on the ball, that is called as reaction force. Both are always equal, but opposite in magnitude, right. Now, try to draw the free body diagram of this small figure. Draw the free body diagram of the ball of the weight W supported by the string AB and resting against a smooth wall at point C. So, the ball is tied at point A. So, tension T A is acting upward and the weight of the ball is acting downward, and wherever the supports are there, we have to consider the reaction forces. So, reaction force is always perpendicular to the floor, right. So, this is R C, right. So, this is R C and this is force or tension, and W which is acting downward, right. This is the free body diagram of the corresponding picture, right. So, now let us discuss a small problem. A sphere of weight 100 Newton is tied to a smooth wall by a string as shown in the figure. As we discussed in our previous slide, the same similar problem, right. Find the tension T in the string and the reaction R. We have to find T and the reaction force R, right. So, let us take, so this is the diagram for this problem, and this is the support of ball. So, let us consider this is C, right, and this point which is called as A, right. Let us take this is point A, right, and weight of the ball is acting downward always, right. This is W and tension is acting upward T A, and wherever the supports are there, we have to consider the reaction force from the support towards the ball, right. So, and this is normal reaction, right, at point C, clear. So, this is the free body diagram, right. See, 15 degree and tension T is acting upward, reaction force towards the ball from the support, and 1000 Newton is acting downward, which is called as W, weight of the ball, right. And we have to rearrange this, right, and find out the included angle between the forces, because here 3 forces are there. So, easily we can apply the Lami's theorem. With the help of Lami's theorem, we can calculate the solutions easily, right. So, the included angle between this R and 100 Newton, which is equal to 90 degree, as we know that already. Then this is 90 plus 15 degree, include angle between R and T. And what is the include angle between T and 1000? 180 minus 15 degree, right. So, easily we can apply the Lami's theorem, and T divided by sin 90, right, and R divided by sin 180 minus 15, and 100 divided by 90 plus 15, right. So, we can calculate, equate these two, then we can calculate T, and equate these two, we can calculate R, right. So, we can solve this problem by another method, that is called as summation of vertical forces, which is equal to 0, and summation of horizontal forces, which is equal to 0. So, with the help of this equation, we can calculate the same T and R, right. See, summation of horizontal forces, summation of vertical forces, which is equal to 0 first. So, T sin T cos 15 minus 100, because the T is acting upward. So, T cos 15 is acting downward and W 100 Newton is acting up downward. So, both are opposite direction, take upward which is positive and which is negative downward, right. So, that is why T cos 15 minus 100 which is equal to 0, T which is equal to 103, the same answer we got, right. Similarly, summation of horizontal forces equal to 0. How many horizontal forces are there? The T is acting horizontally and R is also acting horizontally. So, T sin 15 both are in the opposite direction, right. So, T sin 15 is acting this side, right. So, that is why right hand side, I mean the arrow mark towards right side will take plus and negative which is left side. So, that is why R minus T sin 15 which is equal to 0. So, R which is equal to 26.76, the same answer what we got in the Lam's theorem method, right. So, we can solve any method, we can solve by any method, right. So, draw the free body diagram. So, next problem, it is a simple problem, just we have to draw the free body diagram for this case, right. So, draw the free body diagram of the ball of weight W supported by a string AB and resting against a smooth wall at C. So, wherever supports are there, we have to calculate or we have to take reaction forces. So, at C we have to consider one reaction force, normal reaction force, right, normal reaction at point C. Similarly, D is also one of the support. So, we have to calculate normal reaction at point D, right. So, what is the free body diagram for this? So, this is the ball and this is tension A, TA, right, this is point A and the weight of the ball is acting downward, this is W and normal reaction is acting upward, that is at point D. And similarly, here normal reaction at C is acting towards the ball from support, right. So, this is the free body diagram. See, this is tension and W is acting downward and the reaction force at point D is acting towards the ball and the reaction force C acting towards the ball from point C, right.